Ventilation fundamentally it's the air that we breathe. So we want to make the workers' life better, healthier. So we've put it out to the future generation to come up with perhaps new solutions that us old guys haven't thought of yet. The challenge to the students is to come up with new ideas to fundamentally change the business through better ventilation.
Now, these students have to mine deep within themselves and pitch their ideas to our Dragon's Den-style panel of industry leaders. Can they stand the heat?
Please welcome the Master of Ceremonies, George Flummerfeld.
Okay, everybody, it's time for the main event. The time of reckoning for the finalists as they face a panel of top mining executives and try to convince them that their idea is the best, Dragon Den style. It's time to introduce the first team of finalists. Please put your hands together for Sarah, Peter, and Patrick, who came up with the next phase.
Greetings, everyone. So today we are bringing you phase change material. When we thought of this concept, we were first looking for current heat management products that exist today that we could port to the mining industry. And we found phase change material was a great heat management product because it could store, absorb, and release energy using phase change cycle. The PCM, what happens is we are applying it in the shaft here from 0 meters to 1,000 meters and then 1,000 meters to 1,500 meters. And it will turn back into its solid state. The PCM will be introduced into the shaft in microcapsules. And this will be done within a concrete mortar. Much like you would apply shotcrete to the shafts of a mine, you would apply this mortar. We have the 0 meters to 1,000 meters, that one shaft. We applied A26 there, and then from 1,000 meters to 1,500 meters, we applied A29. A26 denotes the fact that the melting point of that PCM is at 26 degrees, and then the same for A29. The melting point is 29 degrees.
In Northern Ontario, due to the winter temperatures, the PCM will be mostly effective during the months of May to September. So looking at these two graphs, we have the one on the left for a day in July. The orange line represents a day without the PCM, and the blue line represents a day with the PCM. So what happens is the PCM will go back from liquid state to solid state, and this will release heat, therefore bringing the temperature up by 5 degrees Celsius. The cost for the A26 section will be $1.37 million. The cost for the A29 section will be $704,000. And the cost for the mortar application has an application cost per volume, so in total would give us a total cost of $6.36 million. We chose this because there's only one application and it goes through 10,000 phase changes, therefore it would have a lifetime of 27 years. There's no operation cost, there's no energy cost because it's a natural absorbent, so therefore there'll be less of a carbon footprint and it would be a greener approach to mining. Thank you.
Can I ask, in the research you did on this, did you consider any reclamation issues around the product? Does it add anything to the reclamation costs of the mine in dealing with the product?
One of the reasons we decided to go with a wax-based paraffin PCM was because that it is a non-hazardous, non-toxic, and this specific one we found, the company is quoted as saying that this brand is non-flammable, so it won't pose any damage to the environment in that way.
I mean, there's potential this could work. Why did you only think of leaving it in the shaft? Why wouldn't you then use it throughout all the development headings in the mine?
You need a lot of heat fluctuation, and in the shaft, that's when you get the biggest temperature difference, right, from the top to the bottom. In the drifts, the temperature does still increase slowly, but not enough to get the full phase change cycle.
In terms of the shafts, they can be hundreds of meters long, and can you maybe speak about how it would be applied or installed in the very deep shafts?
For our approach, we did it the same method you would do if you were doing a shotcrete lining. We decided, though, for what we were doing here, it would be about 4 inches thick, the lining, but using the same equipment, but the same way you would apply shotcrete lining to any shaft.
The only other thing we would do differently is you'd add a PCM with a different melting temperature.
Thank you. Ladies and gentlemen, please put your hands together for the next phase. Please welcome Joshua, Alex, Adam, Liam, Mohammed, and Justin from the team Pipe Dreams.
Judges, audience members, and to the millions watching at home and abroad, I am Adam.
And I'm Josh.
And we've come to say 3 words: deep lake cooling. We're all here for the same reason. As mines go deeper, the temperatures rise. LaRonde is pushing 3,000 kilometers. Sorry, it's past 3,000 kilometers. Kid Mine gives their tour groups t-shirt coveralls, and it's so hot at the bottom of the ramp at Macassa that, as the miners like to tell me, "Oh, you can fry an egg right off a scoop there, bud." That's where our cooling solution comes in. It's feasible, it's safe, and it takes advantage of our most important natural resource: water, and without polluting it. No cooling chambers mean that there are going to be lower airflow requirements. No expensive refrigeration units means that there's going to be lower capital costs. And cooler miners are less likely to pick on the summer students.
So how this works is that frigid water, around 5 degrees Celsius, will be pumped from the bottom of the nearby lake and sent via a series of boreholes to the bottom of the mine. Here, this water will be utilized in spray chambers to cool the air. There'll be 2 spray chambers, one at each of the 2 new ore bodies. Here, there'll be a heat exchange taking place between the cold water and warm air, thus significantly increasing the temperature of the water. This water will then be pumped back up to surface, will make its way into a water treatment facility, and then be sent back into the lake. This now cold air will make its way back into the inner workings of the mine and cool the mine in conjunction with provincial regulations.
Over the course of an entire year of operation, only 1% of the water that's inside the lake that we've selected will ever actually make it through the system. Our design is very feasible as well. Only $28 million is the capital cost that we've estimated. This includes our pipeline infrastructure, our pumps cost, our borehole developments.
So in conclusion, we'll actually require significantly less ventilation infrastructure development due to the elimination of conventional refrigeration chambers as well as underground cooling towers. So we think that that will result in a 58% reduction in power requirements. Questions?
The processed water that's rejected from the spray chamber, did you give consideration to whether that could be used underground as the processed water?
Yeah, I guess it could be used again underground.
You did make reference to putting cleaner water back in the lake, but sometimes that's not always good as well. So I guess what your thoughts were on.
Yeah, it's true that maybe they don't want Aquafina going back into the lake. I imagine that we could maybe work with some bio monitoring groups to try to maintain the natural state of the lake.
Add to the Dragon's comments. Great presentation, guys. Very compelling and engaging. $28 million for the capital, and I think you said $750,000 was the total operating cost.
That's right. Yeah.
$750,000 sounds keen. Yeah, if you can come and build a water treatment plant for me for $28 million, I'll hire you tomorrow. So.
Good point.
Ladies and gentlemen, put your hands together for a great presentation. Pipe Dreams. Well done. Representing the University of Toronto, we have Yoko, Marina, Matt, and Justin. Come on in. This is team named Safe Through Sound.
Good afternoon, ladies and gentlemen. Dragons. We are Safe Through Sound. We're here because underground mining continues to go deeper, higher stress, hotter conditions, and we're straining the economic and technical limits that we're at right now. The solution that we have is acoustic agglomeration. Acoustic agglomeration uses sound energy or sound waves at an ultrasound frequency in order to collide the particles, and they agglomerate together. This results in a particle size increase roughly in between 4 to 7 times. And why is this important? It really makes these particles that are ultrafine or fine particles manageable. Where can we use this in the mine, and how do we get it there? So we say it as a 2-phased approach. The first one will take 2 to 3 years, and that's really to kind of de-risk the technology, figure out where it can be used and should be used. And where does this look like in a couple years? Really trying to find the full potential of this technology. We see it as lower operating costs in your ventilation systems. We also do see it as a very versatile technology. However, the one that we see moving forward right now and we've decided to explain is controlled recirculation. So controlled recirculation, you have a mine 2.5 kilometers deep, you have to send air down, it gets used through the working environment, and it gets sent up. We think that acoustic agglomeration is an essential step in this chamber, and it allows the feasibility for this system, and or enhances the economics. So the big thing now, what does it mean economically? Big money, does it actually make money? And the Lakeview mine, we did our case study on, when you add 11% recirculated air goes through our chamber, it results in an IRR of just under 8% and a payback of just under 7 years on an investment of $750,000. So where do we see acoustic agglomeration? Just to sum it up, we think it's a technology that is disruptive and has potential in the mining industry. We think that it's absolutely essential that you three should be considering it in your business, in your operations, and within the mining industry. Thank you very much.
So, not familiar with acoustic agglomeration, strangely enough. I thought it was the name of a band. The research into the health and safety side of this, does it have any implication? Just talk to me about how you looked into that.
Well, right now, since the past 10 years, there's been a movement in the diesel engine technology to increase the efficiency of diesel consumption. Sure. So what that's actually been doing that hasn't been noted from the ventilation perspective is that there's a lot more particles that are smaller being produced by these engines. Yep. The exposure levels are a lot worse for the miners, and it's unsafe conditions that are being produced, and acoustic agglomeration actually tackles that issue.
Sure.
Today we see a lot of research and kind of the next wave being changing the technology to batteries, and wondering why you didn't kind of go down that route in terms of the battery operated.
That's number one on our risks. Absolutely, it's a huge risk is battery electric fleets. With an existing fleet, this technology may enable you to not save that capital to switch over to an electric fleet. So this is one of the options. We do think there are other options, but we think this technology just needs to be looked at.
How you physically see adopting it? Are you thinking it's going to be added to equipment, or is it something in a certain part of the mine?
We're advocating for looking into small pilot scale, applications similar to, mimicking the automotive industry, incorporating this into diesel engines, and then moving forward with larger visions.
Thank you, Team Safe Through Sound. Please thank the team, University of Toronto. Thank you, well done.
So, I think the protocol is that we go third, second, and first. Right. And I have the privilege of talking about the third place team. The third place team is the Acoustic Agglomeration team. And I say the privilege because I think it was a fantastic presentation. It's an excellent technology, and I really do think it has application. So congratulations for the area you've looked at.
All three ideas, what I look at, I see as something that's things that we could work with in our industry. But where we picked for the second place team, which was the first team, the PMC or the paraffin wax, I think that it's very innovative. It's probably the most innovative idea there, and it has a lot of applications. Maybe we just need to do a little bit of work on some of those things. But we looked at number two. The PMC as the number two team.
So we selected the pipe dreams as the winner, and really we thought that it did the best at answering the challenge that was posed to the team. And it's a very simple idea, but sometimes simple is really the best way to go. And we thought it was a very good presentation. But again, congratulations, because they were all really good presentations and all really good ideas that certainly made our job very tough. But congratulations to pipe dreams.
We're now going to reveal the results of the audience vote. And the winner, in a close race, the next phase. Well done to the next phase. Congratulations. I'd invite you now, please come on stage to receive your awards, all three teams. So the third place check for the Acoustic Agglomeration team.
No, team.
Tony McCooch will present to the next phase. Well done. And Jennifer to Pipe Dreams, winning team.
Thanks to OMA, thanks to the Dragons for taking their time. And I think it was really cool just to look at it differently, right? Anything was on the table for this this competition. Anything is okay, and we're getting involved. So thanks for inviting Toronto to the team.
Once again, I just want to thank the OMA staff. This was such a great opportunity, and I'm glad this is the first time brought to the schools, and this was a great competition. Thank you, everyone.
Great job.
And a big thanks goes out to our group. We put in quite a bit of work into this, long nights to get this going. And yeah, just want to say thank you. Thanks, everyone. And thanks for coming out.